Hello. Hello dear students. So welcome to Wallah. Today we are going to cover system analysis using Fourier transform, the continuous time Fourier transform. Okay. So let's begin the series. We'll be doing inverse Fourier transform, the system analysis using Fourier transform, and the type of filters. Out of these three, the most important is type of filters. Okay. And we'll be also doing the Hilbert transform. What is Hilbert transform and what is exactly the use of Hilbert transform? We'll be looking at that also in this lecture. So first of all, how to find out the inverse Fourier transform. In the last class, we studied how to find out the Fourier transform. Here we will see how to find out the Fourier transform. Now there are two methods, there are two cases here. We have two cases. We have two cases. The first case is if the Fourier transform is written as a polynomial in terms of j omega. If the Fourier transform is known or is written in terms of j omega. So if the Fourier transform is written in terms of j omega or a polynomial in terms of j omega, then we can apply the inverse Laplace transform. We can apply the inverse Laplace transform in such cases, and we will find out the inverse keeping in mind that ROC must include the j omega axis. Okay, so we will find out the inverse Laplace transform keeping in mind that the ROC include the j omega axis. Okay, so ROC must include the j omega axis, that is the requirement here. Okay, now if for example, the example for this case is, suppose it is written that x omega is equals to 1 upon j omega minus 5. Okay, so this is a polynomial function, polynomial in denominator, right? So we can like convert, we'll write j omega as s, we'll write j omega as s, so we'll write this as s minus 5. Now since the pole location is at 5, we can have two ROCs, sigma greater than 5 or sigma less than 5. So we'll choose the ROC that is sigma less than 5. So we'll take the signal, or the signal will be left-sided signal. We'll create a left-sided signal from here, and it will be equal to minus times of e to power 5t u of minus t. Okay, so we'll create this signal minus times of e to power 5t u of minus t. So in any equation, if we have a polynomial function of j omega, we'll use Laplace transform for finding the inverse. Always remember that. Okay, so I hope this point is clear to all of you. This is case 1. We have another case. When the x omega or the Fourier transform is written in terms of a signal, in terms of a signal of omega. Okay, when x omega is written as a signal of omega, then in that case we cannot apply this method of Laplace transform. We will apply the inverse Fourier transform formula, that is xt is equals to 1 upon 2 pi minus infinity to infinity x omega e to power plus j omega t d omega. Okay, we'll apply this formula. We'll put the Fourier transform here and we'll integrate it to get the result. Okay, so I hope this is clear to all of you. I have one example here for more clarity. Okay, I have one more example here for more clarity. So here we can see that the Fourier transform is not written as a function of omega or as a polynomial function of j omega, So we cannot use the inverse Laplace transform or case 1. We will be using case 2, that is the inverse Fourier transform formula. So what is the formula? The Fourier transform is given to us. It is u of omega plus 3 minus u of omega minus 3. Now we all remember what is the u. U is a unit step function. So u of omega plus 3 minus u of omega minus 3 will be a rectangle from minus 3 to 3 in omega domain. Okay. So xt will be 1 upon 2 pi minus infinity to infinity okay, we have to perform this integration. So this is equals to 1 upon 2 pi minus 3 to 3 means we can integrate this. We can, since this x omega is only non-zero from minus 3 to minus 3 to 3 on the omega axis, so the integration can be from minus 3 to 3. This is 1 and this is only e to power j 3 omega. Now we'll integrate in terms of omega. That's a very simple step. Now nothing else is required here. We have to integrate. We'll take j omega or omega common. Now we'll integrate this. Now when we'll integrate this, we'll get 1 upon 2 pi. We'll put this constant term down, because why this is a constant? Because we are integrating in terms of omega. So this will be j t plus 3. And here we will get, in place of omega, we will put 3 and minus 3. We will get so from here we can see that we will get, this will become a sine term, right? This will become a sine term. This will be the, sorry, j will not be there. J will not be there because we can see that this term divided by 2j will become a sine term. Okay. So I hope all of you are able to get this. Yes. So this is the result that is very important, and I hope you are able to get this. Okay. So this is the Fourier transform, and we can see that we have to apply the formula. Okay. Suppose we have this signal. Let me take one more example for more clarity. Suppose we have this signal, x of omega is equal to 1 upon j omega minus 5 j omega plus 3. So this is polynomial in terms of j omega. So we will never apply the inverse Fourier transform in this formula. We will convert this into Laplace, and then we'll apply the inverse Laplace transform, and we'll keep the ROC such that the ROC include the j omega axis. That's it. So we'll convert this into Laplace, 1 upon s minus 5 s plus 3. Now we can see that there are two poles, one at 5, one at minus 3. Okay, one at 5, one at minus 3. So we can see that the ROC is between minus 5 and 3, because we need to include the j omega axis or sigma equal to 0. So we'll keep the ROC minus 3 to 5, minus 3 to 5. Okay. Now we'll keep minus 3 at right sided and 5 will be left sided. Okay. So we can take the partial fraction now and we'll get the result. Minus 1 by 8 s plus 3 perfect. So this will be the result. Okay. Now, um, is the partial fraction correct? S minus 5, S 1 by 8 is correct. Okay, so partial fraction is correct. I have written there, here I have written wrong. So it is S minus 5. So partial fraction is correct, everything is fine. Okay. So now we can see that this is left sided and this is right sided. So we can convert it into time domain signal. Minus 1 by 8 e to power minus 3t ut minus 1 by 8 e to power 5t u of minus t. So this is how we can easily find out the inverse Fourier transform of any Fourier transform given to us. Okay. So we have seen the examples. Now we'll move on to the signal transmission through the systems. Okay. So exactly similar things we have seen in the Laplace also. We have the LTI system. We have the LTI system with impulse response HT. Okay. So the Fourier transform of HT is called H omega. Now here three terms are very important. HT has Fourier transform H omega. The name of H omega is the frequency response of the system. Okay. Frequency response of the system. Magnitude of H omega is called the magnitude response of the system. Magnitude response. And angle of H omega is called the phase response of the system. Phase response of the system. Okay. So this is, I hope all of you are able to get this. Now, this is the LTI system. If we put input as xt, the filter has the impulse response ht. The output is ht convolve with xt. ht convolve with xt. Okay, we know this. Now, if we convert or if we apply the Fourier transform formula or property here, if the input Fourier transform is x omega, filter has a Fourier transform h omega, the frequency response. Then using the property of Fourier transform, convolution in time domain is multiplication in frequency domain. So we can see that in frequency domain, the output will be multiplication of these two. So we can say that y omega is equals to x omega into h omega. Okay. So this is the important formula here. Great. Now, suppose we have this kind of questions. So these kind of questions are solved by Laplace. Any differential equation, this is a differential equation. Any differential equation, never solve it using Fourier. Always solve it using Laplace. Okay. So I'll solve this question for you just for sake of example, that this kind of differential equation, solve it using Fourier. Okay. Solve it using Laplace only. Okay. So suppose this is the differential equation given to us. Okay. We have to find out the frequency response of the system. So frequency response is very easy. First of all, find out the Hs, the transfer function, and replace S by j omega. So how to find H omega? First of all, find out the transfer function and replace S by j omega. Okay. Replace S by j omega. That's it. Okay. So we have to find out H omega and the impulse response Ht both. So we'll solve this question. Let's solve it. Suppose this is the system equation. We'll first of all take the Laplace transform. So S square ys plus 4s ys plus 3ys, okay, is equal to s xs plus 2. Okay. Now, we will now take ys upon xs. Okay. So this is your hs, the transfer function, and when we will convert it into h omega, we can see that it will be written as 2 plus j omega. The only thing is, whenever we are doing this, we will keep the ROC of the Laplace transform as such that it contains the j omega axis. Okay. So this is h omega. Now here we can see that the roots are -1 and -3. Okay. The poles of this are -1 and -3. Okay. So what kind of ROC we will choose? We will choose the ROC such that it includes the j omega axis or 0. So we will choose the ROC sigma greater than -1. Okay. So we will choose this ROC sigma greater than -1. When we'll choose this ROC sigma greater than -1, we'll keep both the poles as right sided. Okay. So to find out the HT, the impulse response, we have to take the inverse. So we'll take the inverse. First of all, we'll take the partial fraction. This is 0.5 upon s plus 1. Great. And 0.5 upon s plus 3. Now, since the ROC is this one, sigma greater than -1, both the poles are right sided, we can easily get the HT, the impulse response of the system, that is both side pole right sided, 0.5 e to power minus t, e to power minus 3t ut. This is the impulse response HT of the system. I hope this is all clear to all of you. Great. So this is how we can find. Now, how to find out the output for this input? That is also very easy. You simply have to find out the ys. Hs into xs, and you have to find out the inverse. That's it. Okay. So the only concept here is, whenever we are solving the differential equations, always solve using Laplace. Never solve using Fourier transform. Okay. Now the concept of the ESD, that is the energy spectral density of a signal. So many a times in a question we have to find out the energy spectral density of a signal. Now that's a very simple concept. The concept is, energy spectral density of a signal is equal to magnitude of Fourier transform square. Okay. Magnitude of Fourier transform square, or square of the Fourier transform of the signal xt. Okay. So magnitude of x omega whole square. Now suppose we have any system where input is xt, output is yt, the impulse response is ht. Okay. Now here we can see that we also know, if the input is x omega, here it is h omega, the output will be y omega, that is x omega into h omega. Okay. Now the energy spectral density of input will be, mod of x omega whole square, right? The energy spectral density is Fourier transform mod square. the energy spectral density of output will be mod of y omega whole square. Okay, so how you write this mod of y omega whole square, that is important. Okay, so that concept I am going to tell you. So mod of y omega whole square is written as mod of h omega whole square into mod of x omega whole square. Okay, so we can say that energy spectral density of the output is equal to mod of h omega whole square multiplied by energy spectral density of input. Okay, so this equation is important, that whenever we want to find out the energy spectral density of the output, that is simply equal to energy spectral density of input multiplied by mod of h omega whole square. Okay, so this we can find out, or this we can use to find out the energy spectral density of the output. Now, using Parseval's we can find out the energy of a signal from its energy spectral density. Okay, so energy of a signal is equal to 1 upon 2 pi minus infinity to infinity energy spectral density of the signal d omega. Okay, remember this. This is directly from the Parseval's theorem only. Okay, so Parseval's theorem is also exactly similar to this. Energy of a signal is equal to 1 upon 2 pi minus infinity to infinity energy spectral density d omega. Okay, so I think you all will remember this formula. This is very important. Now let's come on to the topic, that is distortionless systems. What is a distortionless system? So distortionless system means whenever any signal passes from a system, then the output should be distortionless. That is, the system does not distort the signal. Now what does it mean? It means that whenever any signal is provided as input to the system, then at the output, the shape of the system should not be changed. Or we can say that the output shape and the input shape should be same. The shape of the output and the shape of the input should be same. So if xt is given as input, the system is distortionless. The system is called distortionless when shape of the output is equivalent to the shape of the input. The shape of the output is same as the shape of the input. Okay, now if xt is given as an input, then output should have the same shape. Now means that the output of the system should be equal to a constant multiplied by the input or its delayed version. Okay, so then only the shape is not changed. Okay, if we multiply the input by a constant, then the shape will not change. If we delay the input by some time, then also the shape will not change. So this is the condition, that the output should be k times the xt minus td, means input has some delay and input is got multiplied by a constant k. That's it, nothing else is required here. This is the condition for the distortionless system. Now this is the condition in time domain, but how to see the frequency domain of this distortionless system? So let's see. We can see that the output yt is equals to k is any constant, k times of xt minus td. So we can say that y omega is equals to k times of x omega e to power minus td omega. So here we can see that we are applying the time shifting property of Fourier transform. Now from here we can see that y omega upon x omega is equal to h omega is equal to k e to power minus td omega. This is the frequency response of the distortionless system. So from here we can see that the frequency response of the distortionless system should be of the type, the frequency response of the distortionless system for a distortionless system should be like this, k e to power minus j omega td. Okay, now here we can see that the magnitude of h omega, the magnitude of h omega is constant equal to k. The magnitude of h omega is constant equal to k, means it is constant for all the frequencies, and the phase is minus omega td. So remember that magnitude response is constant but the phase response is linear. Linear means with it is proportional to omega. It is proportional to omega, and magnitude response is a constant. So we can see this with the help of a figure also. If we draw the magnitude response, so it is a constant, right? It is a constant. Magnitude of h omega, it is a constant k. Okay. And phase response is linear. Sorry, it will be like negative. It will be like this. So phase response is linear. Phase response is linear like this. Okay. So this is all for the distortionless system. This both are with respect to omega. Great. Next, group delay and phase delay of a system. For this topic, you only need to remember two formulas. Okay, that is, if an equation, a system is given, okay, you have to find out the group delay and phase delay, then we can directly apply the formula. You only need to remember the formula for this topic. Okay, if you remember the formula, if you know the formula, you are done. Okay, that's it. Great. So the formula is phase delay, that is tau p is equals to minus the phase of h omega divided by omega. So if they are asking a phase delay at a particular frequency, simply apply that frequency here at a given omega, at omega equals to omega naught, or any frequency which is given in the question, you can apply that frequency and get the result. Similarly, group delay, at a particular frequency we have to find, that is omega equal to omega naught. Okay, so this is all for the group delay and phase delay. Only you need to remember the formula, that's it. Nothing more than this is required for the group delay and phase delay. Okay, now we have seen the concept of eigenvalue and eigenfunctions in Laplace transform. The same exactly similar concept is here in the Fourier transform also. So the Fourier transform concept is like this. Suppose if we have any filter, LTI filter or LTI system HT and has Fourier transform or frequency response H omega, and if we are giving input xt, if we are giving input xt of this format, e to power ct, okay, e to power ct, or better to write it as e to power j omega t, j omega naught t, then the response is e to power j omega naught t multiplied by h omega at omega equal to omega naught, okay, e to power j omega naught t multiplied by h omega at omega equal to omega naught. Similarly, if we have input e to power minus j omega naught t, then the result will be e to power minus j omega naught t minus omega naught, okay. So these are the two equations that are very important. Similarly, if you remember, if you recall the concepts of eigenvalue and eigenfunction, so the cos and sine are eigenvalue only if HT is a real. So if the signal is real or the impulse response is real or the system is real, then only this sine and cos are eigenvalue and eigenfunction. So if HT is real, then if the input is sine omega naught t or cos omega naught t, we will find out h omega at omega naught. We will find out h omega at omega naught. So let us say h omega at omega naught is equal to a angle theta, means h omega at omega naught is equal to magnitude a and angle theta. So the output will be, we will multiply this with a and okay. So these are a sine omega naught t plus theta and a cos omega naught t plus theta, okay. So this is how we can solve any problem. There are many problems asked on this concept in GATE exam, okay. Great. Now what is Hilbert transform? So Hilbert transform, you need to remember only two things for Hilbert transform, that is its impulse response and its frequency response, okay. Only two things, impulse response and the frequency response. So if you recall, first of all, signum t, if you remember signum t Fourier transform is 2 upon j omega. I told you to remember this in the last class. Now apply the duality. So it is 2 upon jt 2 pi signum minus omega. 2 pi signum minus omega, okay. Now signum was in odd function, so this minus sign will come outside, 2 and 2 will cancel, pi will go down, 1 upon j pi t will have minus signum omega as a Fourier transform. If we multiply j both sides, we will get 1 upon pi t will have Fourier transform minus j signum omega, okay. So this, if we have a LTI system, if we have a LTI system, if we have a LTI system with impulse response equal to 1 upon pi t, means this, if we have a LTI system with impulse response 1 upon pi t, then this system is called Hilbert transformer or Hilbert transform, okay. So anywhere you see this Hilbert transform written, assume that or just replace it with the LTI system, that is having the impulse response 1 upon pi t, okay. So that is very important to remember this. Now what is the property of this system? The property of this system is if the impulse response is 1 upon pi t, the Fourier transform will be h omega will be minus j signum omega, minus j signum omega. Okay, so this you have to remember two things, the impulse response and the Fourier transform, minus j signum omega. So how will be the h omega? H omega we can say, if you remember the signum function, so it is minus j signum omega. So it will be minus j when the omega is positive and plus j when the omega is negative. Minus j signum omega. Okay, so this is how it is. Okay, h omega. So remember this, Hilbert transform means Fourier transform is this and the impulse response is 1 upon pi t. Okay, so you have to remember these two things. Now, before moving ahead, one very important concept of Hilbert transform. So, suppose this is Hilbert transform. The impulse response is 1 upon pi t and the h omega will be minus j signum omega. Okay, so I hope you remember this. Now, if the input is, let us say, cos omega naught t, cos omega naught t, okay, then we know that since this is ht is real, right? The impulse response is real, it is never complex or imaginary. So since ht is real, we can say that the Fourier transform h omega, the Fourier transform h omega will be like this. Now, what will be the magnitude or value of h omega at any omega naught? At any frequency omega naught, what is the Fourier transform h omega? H omega at any omega naught, we can see that it is minus j. It is minus j. Minus j means magnitude 1 angle minus 90 degree. So if we put this magnitude 1 angle 90 degree, so we will multiply the input by magnitude and we will give a minus 90 degree phase shift to the input. Okay. Similarly for the sine also, if the input is sine wave, then output will also be like this only, multiplied by 1 minus 90 degree. So here we can see that this Hilbert transform acts as a 90 degree, minus 90 degree phase shifter. Okay, so it is simply giving minus 90 degree phase shift to the input. So remember this very important characteristic for the Hilbert transform, that is Hilbert transform is minus 90 degree phase shifter. Okay, it is minus 90 degree phase shifter. So remember this property, very important. Okay, so now let's move on to the how to determine the type of filters. So first of all, let me tell you what all filters we have. What all filters we have? We have low pass filter, high pass filter, band pass filter, band reject filter and the all pass filter. So we have these kind of filters. The low pass filter, high pass filter, band pass filter, band reject filter and all pass filter. Okay, so what all characteristic we have? So if we have a low pass filter, the characteristic of the filter or h omega, the transfer function of this filter is like this. Means it is non-zero for low frequencies and 0 for high frequencies. Okay, so it is non-zero for low frequencies and 0 for high frequencies. Okay, so this is your h omega. It is non-zero for low frequencies but 0 for high frequencies. So remember this low pass filter. For high pass filter, it is 0 for low frequencies, but it is non-zero for high frequencies. So it is like this. So this is your H omega and this is your omega axis. This is your H omega and this is your omega axis. Okay, so it is 0 for low frequencies and non-zero for high frequencies. Okay, band pass filter. Band pass filter is non-zero only for some range of frequencies. Okay, it is non-zero only for some range of frequencies. And then it is 0 again. So it is 0 at 0 frequency and high frequencies, but non-zero only at a range of frequencies. Okay. Band reject filter. Band reject filter will be non-zero for major range of the frequencies, means it is generally non-zero, but it is 0 for some frequencies only. It is 0 for some frequencies only. Okay, it is like this. Okay, so it is non-zero for some range of frequencies, but 0 for very less range of frequencies. Okay, generally it is non-zero, but 0 for less range of frequencies. Last is all pass filter. All pass filter is never 0, it is constant. Okay, so all pass filter is a constant, has a constant frequency like this. Okay, so I'll tell you how to find out the type of filter. We have a very important and very simple method to find out the type of filter. So let us see how to find out the type of filters. It is very important because these kind of questions are 2-marker questions and they are very easy to solve. So how to find out the type of filter? Let us see the method. Method. So method is step number 1. The step number 1 is replace S by j omega. Replace S by j omega in the HS, in the transfer function HS. Now step 2, find out the H omega magnitude at omega equals to 0. Let us say this is A, and find out the magnitude of H omega at omega equals to infinity. Let us say this is B. So we have to find out the magnitude at 0 frequency and infinity frequency. Okay. Now, if A is greater than equal to 1, if A means 0 frequency magnitude is greater than equal to 1, but B is equal to 0, then it is a low pass filter. Okay, then it is a low pass filter. Second, if A is equal to 0, okay, means at 0 frequency it is 0, but at infinity frequency it is greater than equal to 1. So we can see that this will be a pass filter. Are you all able to visualize this also? That at 0 frequency this is non-zero, a very large, then it is low pass filter. At 0 frequency it is 0, but infinity frequency it is large, so it is high pass filter. If at both the frequencies A is also 0, B is also 0, then it is a band pass filter. Then it is a band pass filter. Okay. Now, if A is non-zero or A is greater than equal to 1, B is also greater than equal to 1, then it is a band reject filter or all pass filter. Okay, so it can be both band reject filter or all pass filter. We have to see the property of all pass filter to finally determine this kind of cases. Okay, so first case, if A is greater than 1, B is 0, low pass filter. A is 0, B is greater than 1, high pass filter. Both 0, band pass filter. Both greater than equal to 1, it can be high pass band reject filter or all pass filter. Okay, so these are the cases that we have to see. Now how to bifurcate or how to differentiate between the band reject filter and all pass filter, how to differentiate between the two. So we have the property of all pass filter. The property of all pass filter is that the property of all pass filter is that the poles and zeros are at the mirror image with respect to the j omega axis. Are at the mirror image with respect to the j omega axis or the vertical axis. Okay, the j omega axis or the vertical axis. So suppose we have this. Suppose we have a pole here. Then if the system is all pass filter, the zero has to be at the mirror image. Mirror image means this location. If the zero is at pole at this location, then the zero has to be at this location. Okay, so poles and zeros are at the mirror image with respect to the j omega axis. Suppose we have all pass filter with zero here, then pole has to go here. If we have a zero here, then pole has to go here. If we have a zero at this location, the pole has to go at the mirror image location. Okay. So remember or recall the properties of poles and zeros for the even cases and real cases in Laplace that we have seen. Okay, so these are the properties of all the type of filters. Okay, these are the properties of all type of filters. Great. So let us find out the type of filters. Okay, let us find out the type of filters. So first type of filter is this. So we'll first of all replace by S by j omega. J omega plus 10 upon j omega whole square plus 5 j omega plus 15. So at omega equal to 0, we can see it is 10 by 15. Okay, it is 10 by 15. At omega equal to infinity, this will be 0 because denominator has infinity square, numerator has only infinity. So this will be 0. So what kind of filter it is? It is a low pass filter. Second, this one. So this we can say it is j omega upon j omega plus 10. So at omega equal to 0, this is 0. At omega equal to infinity, this is infinity upon infinity. Okay, infinity upon infinity, that is 1. So this is high pass filter. Third one. This is j omega square plus 10 j omega plus 100. Okay, so at omega equal to infinity, at omega equal to 0, so we can see that if we put omega equal to 0 here, the numerator will become 0 and the result is 0. So we get a 0. At omega equal to infinity, this will be 1. Because we can see numerator is also infinity square, denominator is also infinity square. So this is 1. So this is also a high pass filter. And the last case. In the last case, we can see that we have a 0 at 10, pole at minus 10. 0 at 10, pole at minus 10. So can we see the poles and zeros are at the mirror image with respect to each other? Yes. Because we can see that if there is a 0 at 10, pole at minus 10, so they are at the mirror image with respect to each other. Thus we can say that this is the all pass filter. The last one is the all pass filter. Okay, so this type of filter is very important case, a very important question that can arise from here. Okay, so this is all for today. We have learned the type of filters, we have learned all the type of filters, we have learned how to find out the inverse, we have learned the distortionless systems, we have learned the group delay and phase delay, we have learned the energy spectral density of input and output. So these all are very important terms that you need to remember for GATE exam. Only formulas are sufficient for GATE exam in these cases. All the best. Bye bye.